Okay, hey everybody. This is going to be the video of review of the first type of test question for the mechanical waves and sound test. As a reminder, here on Google Classroom, if we go to classwork, notes on the left, most recent notes from February 20th. Good Lord. Mechanical waves and sound, there it is. Okay, so if we need to review some stuff, I'll point you to 3 pages on the notes that'll be most useful for this particular question. Vocabulary, yeah, make sure we remember that stuff. Symbols being used for particular quantities, like lambda for wavelength, capital T is period, frequency is reciprocal of the period, their units, all that stuff, right? All right, the wave equation. The wave equation most frequently written as right here, V equals F times a lambda, where V is velocity or wave speed, F is frequency, and lambda is the wavelength. Can also be written as the equation right above it, because frequency and period are reciprocals of one another. These equations, or the wave equation, there's pretty much 2 equations that are the same thing, can be used for any waves. Okay, so we'll be using those for both the test questions. And important stuff is listed here as well, but the other equation that is useful is this equation here for a wave traveling through a string. The velocity of the wave also relates to the force of tension in the string and the linear density of the string. Linear density is mass per unit length. All right, so linear density is what's downstairs under the radical. Little m is the mass of the string. It's a very tiny mass. And then capital L is the length of the string from what we call the mechanical wave driver, the oscillating thing producing the wave, all the way to the little pulley that we use to keep the wave fixed at the other end. So little m divided by capital L is, together, the linear density. You can say the quotient there is the linear density. F sub t we're using for the force of tension. We don't want to use capital T here because we have capital T to stand for period. So these are the 2 main equations. Wave equation, V equals F lambda, and then the wave speed in a string equals the square root of the force of tension in the string divided by the linear density. And the linear density is equal to little m divided by capital L. Let's take a look at the first question here. All right, this one we're going to read through the question, list out the things that we know already to begin with, analyze our picture, answer our questions. So a mechanical wave driver pictured at the left end of the wave, that's my blue thing that I've drawn there. That's the thing producing the wave, produces periodic traveling waves along the string shown below. When we have a standing wave pattern, which is produced in our picture here, you have one wave traveling one direction, that's in red, and then when it hits the pulley over here, that's a fixed point, or node, the wave bounces back. And then when they interact, if you have the right frequency and the right linear density and all these things add up so that you get a nice standing wave pattern, which only happens at certain intervals, then we get a pattern that looks like we have a number of loops just kind of standing there on the string. So it looks like a standing wave. It's 2 waves interacting. Okay, so right now we can see we have 1, 2, 3 loops being formed by our string. What else are we given in our question? The string has a linear density of 0.15 kilograms per meter and a total length capital L equal to 2.5 meters. The mass capital M hanging over the end of the pulley has a mass of 0.90 kilograms. What's up? It's pancake syrup. What are you going to do with that?
I need some syrup in the pancakes.
You need some syrup on the pancakes?
Let's go.
Let's go? Okay, I'll be in a minute. Okay. I didn't know we were eating pancakes. The full length capital L of the string is always going to be from the wave driver on the left all the way to the fixed end at the pulley over there. All right, and that's not necessarily going to be equivalent to the wavelength. The wavelength is going to be the length of the wave being formed on the string. Before we analyze our picture anymore, let's go ahead and just jot down things that we know. So I know that the linear density, is little m divided by capital L. Little m is the mass of the string. Okay, this guy down here, capital M, that's not a string, that's a block. So don't confuse the capital L and capital M and the little m. So little m divided by capital L is linear density, and that's what 0.15 kilograms per meter. Okay, the total length L, capital L, of the string from mechanical wave driver on the left to the pulley on the right is 2.5 meters. So L equals 2.5 meters. The hanging mass, capital M, which is providing tension in the string, has a mass, capital M, has a mass of 0.90 kilograms. Okay, what else do we know? I mean, that's all that's given in the very first paragraph there. All right, let's start with that. Part A, what is the wavelength of the standing wave? Show mathematically or describe with words how you determine your answer. What is the wavelength of the standing wave? One thing we mentioned in class is that you could look at, like if you plot a sine wave, my xy axis there, full sine wave from 0 to 2 pi is like that. That's a full wave. That's going around a circle once, basically. If you have a standing wave pattern, then you get your reflected wave is coming back. So one wavelength is equal to 2 loops, if you like to look at the loops. And in part D, I come back and ask you about how the number of loops is going to change if you change something else. So remember that one wavelength is depicted by 2 loops. For part A, if I look at my picture, I see that I have 3 loops. So for part A, I'm saying what is the wavelength? Lambda equals question mark. I know for every 2 loops I have a full wavelength, and in my picture I have 3 loops in that entire length in orange, capital L. So one way I can write that is I can say I have 1 1/2 wavelengths, lambda's wavelength, so I have 1 1/2 wavelengths because I have 3 loops. That's 1 1/2. Here's one wavelength right there. Boom da boom. There's one wavelength. So here's 1 wavelength plus I have another half a wavelength at the end because I got an extra loop. So 1 1/2 lambdas, 1 1/2 wavelengths equals my total length of the string, capital L. I like to write that as a single fraction. Or you can write it 1.5 if you want. It doesn't matter. It's up to you. 3/2 lambda, or 1.5 lambdas equals L. In part A, I'm asking what is the wavelength. So we're going to solve for lambda. Lambda is 2/3 L. 2/3 the total length. Then we can go and substitute because we know that the length is 2.5 meters. Right, because that's given. We wrote that up here. 2.5 meters is the length of the string. I'm going to write 2.5 as a fraction. Why not? Our units are meters. I can put that in there if I want. All right, if I simplify this, I got 5/3 meters. And you can, if you want to leave it as that, that's fine. I have a number and I have a unit. Make sure we have our units there. But just for fun, let's also write that as a decimal, about 1.67 meters. Okay, both of these are fine answers, and I've shown mathematically how to get that. You want to draw in the picture too, or draw it out, that's fine as well. Make sure you show you're getting a specific value. So for part A, lambda is 1.67 meters. Part B, what is the speed of the standing wave? Wave speed. Well, wave speed is our V. V is the wave speed. So I need to look, I only got 2 equations really. I can use V equals F times lambda. That's my wave equation. Now I know lambda. Cool. I want to find V, but I also don't know the frequency right now, so this equation, 2 unknowns, 1 equation, not too good. We have our other equation, V equals square root force of tension, Ft, over the linear density. Little m divided by L is our linear density. We do know the tension force, or do we? We do. We got to figure it out, but we know because we know the mass of the hanging block. And we do know the linear density. That's straight up given as 0.15 kilograms per meter. So I can calculate the wave speed with this equation. V is going to be the square root of the tension force divided by the linear density. What's the tension force going to be? If I have this wave generator and this standing wave pattern happening on this string, this mass hanging here is what's keeping the string taut, or keeping it full of tension. How much tension does it have? Well, our mass here is just sitting there, it's hanging, not accelerating, so it has a gravitational force, Fg, pulling down, and it has an equal amount of force, Ft, pulling up. These need to balance, otherwise the thing's accelerating. So it's just balanced sitting there. My tension force has to equal to the gravitational force pulling on the hanging block, capital M. Fg equals what? Mg. Yeah, it's capital Mg. It's not little m. Little m's the string. Okay, capital M is the block. Make sure we don't confuse those. Therefore, the tension force must be equivalent to capital M times little g. So here we go. I've got tension force upstairs, which is capital M times little g, divided by my linear density, which is m over L. I'll leave it as these guys for right now. But this is all I need to figure out the tension force. Now I can substitute. Remember that for little g, you can use 9.8, or we can round in our problems and test 10 meters per second squared is fine. So v wave speed is square root. What's the mass? 0.9 kilograms. That was given. Okay, so I got 0.9 kilograms times 10 meters per second squared over linear density is 0.15 kilograms per meter. My units there. Okay. We can, I think I'm just going to solve this as a, no, we'll do fraction and thing. So 9 times 10 is, 0.9 times 10 is 9, obviously. Kilogram, this is kilogram meters per second squared, or newtons, because it's force, divided by 0.15 kilograms per meter. We get a, I'll just find out what that decimal is right now. We can also use our fraction abilities to get a value. If I solve that, now be careful, you're just going straight to your calculator. You're making sure it does the order of operations properly. There's the wave speed if I just solve that with my calculator. You could also go this way and be awesome and be like, wait, I'm going to do fractions. So I got 9, let's get rid of those units for a second. 0.15 is 15 hundredths, so 15 over 100. Well, that's the same as 900 divided by 15. What's 900 divided by 15? Oh, well, 6 times 15 is 90, right? Alright, so 900 over 15 is 60. So the velocity is the square root of 60 meters per second. Kaboom! Okay, so there's an exact answer. Either way is fine. Make sure you keep the units. Box the answer, please, to make it clear. We're on part C. Moving right along. What is the frequency of the standing wave? Show how you got it. Well, remember we got these. We have our two equations: v equals f lambda and v equals square root tension force over linear density. We've just found velocity, so now we know lambda and we know velocity. So what do we want to find? Frequency. So let's use this guy right here. Let's solve for f. F equals v over lambda. The velocity is, we go with our decimal answers first, if you like. Yeah, we're having a round. That's okay. Let's use a reasonable number of digits. No idea what this quotient is. 7.75 divided by 1.67 is 4.64. So 4.64 units are. Notice the m's for meter cancel out, and I'm left with 1 over seconds. 1 over seconds. That's a perfectly fine unit for frequency. We'll usually just call that hertz. So I'm just going to write it as hertz, Hz. All right, so there's my frequency, 4.64 hertz. No problemo. If we wanted to do that with our fractions, we can do that as well. Our velocity was square root 60 meters per second divided by a wavelength of 5/3. All right, so this is meters per second over meters again. And so I've got 3 square roots of 60 over 5 hertz, because this is inverse seconds. And is there anything, can we simplify that anymore? I don't think so. Huh? Is it 60? Oh, it's 6 square roots 15, right? Because we got 4 times 15, so I could simplify this. I should probably do that. So this is the same as 3 times square root 4 times 15 over 5, right? See what's happening here? So I'm going to take square root force 2. So I have 2 times 3 times square root 15 over 5. So the frequency is also 6 square roots of 15 over 5. And that's in hertz. I can always double check that and put that in my calculator, make sure I'm not going nuts. And see if that is the same. 4.64 is going to get again. Okay, so there's part C. We have our frequency. Part D. The hanging mass, capital M, is replaced with 1/4 of the mass, but frequency stays the same. How many loops should now be formed on the string? Remember our number of loops, 1, 2, 3. Number of loops and wavelength go hand in hand. So every 2 loops is 1 wavelength. So if I change this hanging mass, I end up changing the wavelength. And if you change the wavelength, that means you're going to have a different number of loops that appear in the string. Kind of shorthand conceptual answer, if I decrease the mass, I get more loops. If I increase the mass, I get fewer loops. And so we can show that a number of different ways. I think just like conceptually going over it's very important, but it's also perfectly fine to just recalculate everything. That takes longer and I don't like to do it, but you could. Let's go back to our block. This is the thing that's changing. We're going to have a new tension force. Tension force is equal to capital M times little g, but now we have 1/4 of the mass. Let's reread that part again. It's replaced with 1/4 the mass. So that means you have less mass. Be careful. It's just 1/4 of what capital M was before. So it's 0.9 kilograms divided by 4 is how much the mass is. So I'm going to have 1/4 the tension force. This is the new tension force. It's going to be 1/4 the tension force. Let's just think about conceptually what happens. You can go ahead and calculate that. Like you could calculate what is the new tension force and use that to determine what's the new wave speed, and then use that to determine what's the new wavelength, and use that to say how many loops there are. But we're just going to look at thinking about it conceptually first. So part D, I still have 2 equations, V equals F lambda, and then V equals tension force, square root tension force over linear density. Be careful, the mass that's changing, capital M, is not this mass. It is not that mass. That is the mass of the string. Remember, our tension force is capital M times little g, and that capital M, this capital M mass, is the one that is now smaller. In fact, it is 1/4 of what it used to be. So if I have 1/4 the tension force, if tension force goes down, my velocity is going to go down. I come over here to the other equation. If velocity goes down and frequency stays constant, go back and look at the question again. Frequency is staying constant. If velocity goes down, but frequency is going to stay the same, then lambda must also go down by the same amount. That's our key here. So once we know how much lambda changes, we can say how many loops will be there. Because if the wavelength gets longer, then we'll have fewer loops. If the wavelength gets shorter, then we will have more loops appearing on the string. All right, so we'll go ahead and we'll see exactly by how much that's changing. If I have 1/4 the tension force, represented here by mg, the gravitational force of the hanging block, I have 1/4 of that, and that 1/4 is under the radical. I'm going to have the square root of 1/4 upstairs. If you want to see that mathematically, specifically, then you can say, that's another way to write this. I could say I have square root 1/4 times square root, capital M times little g, divided by square root m over capital L. In other words, I have square root 1/4 times the original force of tension over m over L. This is just showing that this coefficient 1/4, representing our new amount of mass and new amount of tension force, can be pulled out in front, and I can say the square root of 1/4, what is that? That's 1/2 ft m over L. So this is our new wave speed. If I have 1/4 the mass, I therefore have 1/4 the tension force. the square root of that 1/4 is 1/2. So if I have 1/4 the tension force, I now have 1/2 the wave speed. Okay, so another way I could say that, I could say my new wave speed, new wave velocity v, is 1/2 the original wave speed. So my wave speed has gone down. It is now 1/2 of what it was. I come over here to my other equation, which means I also must have 1/2 the wavelength. So wave speed goes down, the wavelength goes down. It gets shorter. Because my mass is 1/4 of what it was, my tension force is 1/4 of what it was. And therefore my wave speed, my new wave speed, is 1/2 of what it originally was. It's 1/2 because I've got that radical there. 1/2 the velocity, 1/2 the wavelength. So now you can go back to your picture and we can say, look, this was our original wavelength. Our original wavelength when we had 3 loops, right, like this. Our original wavelength was from here to here, right? That's the original lambda, original wavelength. If now we have half the wavelength, let's break that in half. That's right there. Now our wavelength is going to be from here to here when we have 1/4 of the mass hanging off the edge of the string. 1/4 of the tension, we have half the wave speed now, and therefore half the wavelength. So here's our new lambda. It's going to be right there. Well, if that's the wavelength, then I've got 2 loops right there, because a full wavelength is equivalent to 2 loops. And that means you're just going to have 2 loops where all of these original 1 loop, oh, those are some crazy loops. What just happened? Let's try that again. That's a little better. Right, for every one of these loops, I now have 2 loops, because my wavelength is half what it originally was. So you can see now we have 1, 2, 3, 4, 5, 6. All right, as a hint, these answers for letter G will always be whole number values. So you can go back and calculate this stuff, like finding the new tension force, getting a specific value for that, calculating the new wave speed. But you're going to be rounding if you're using decimal values. So you might end up with like 5.94 loops is what you should have, or whatever it's going to be. And that needs to be rounded to 6 because you can only have whole numbers of loops. You can't have like 0.96 of a loop or whatever. So now I go from 3 to 6 loops. So if I 1/4 the mass, I have half the wave speed. I'm going to get double the number of loops. All right, if we were to increase the mass, if we had 4 times as much mass, or if we had 9 times as much mass, then we're going to have a fewer number of loops. You still have to be careful to take that square root, as we did right down here. Take the square root of that coefficient. If I have 1/4 the mass, I now have 1/2 the wave speed. If we have 1/2 the wave speed and frequency stays the same frequency, then I'm going to have 1/2 the wavelength. That's a requirement if frequency is going to stay the same. If I have 1/2 the wavelength, the waves are shorter by half. You can go back and look at your picture. If my original wavelength was from here to here, half the wavelength is now going to be here to here. How many loops are it going to take to get all the way to our pulley, the other fixed end? So our answer here for D is going to be 6